Okay, so you train VLMs, vision language models, right, on short clips.
Yeah.
And yeah, they nail it.
They get pretty good at those quick hits.
But then you throw a 10-minute game at them, maybe an hour-long vlog, and uh-oh.
It's a whole different ballgame.
Suddenly, yeah, temporal gaps, those subtle spatial tracks, hidden goals maybe in a strategy game, they just like slip right through.
But the connections aren't being made across time.
Yeah. You're left kind of wondering, why can't these super smart AIs grasp the full story? They get the snapshot, sure, but the unfolding narrative, the long game, not so much.
The common frustration in the field.
It is. It's the researcher's lament, right?
Yeah.
You're pounding your desk. But then, something new. You build LongVideo-Reason.
Yeah.
104,000 QA pairs, chain of thought annotations, across sports, vlogs, games. You train it on, what, 36,000 high-quality reasoning steps?
A massive curated data set.
And suddenly, they start connecting frames step by step. Okay, so you've got to be wondering, how did they actually pull this off? Let's unpack this.
Exactly. And this isn't just a small tweak. It's really a comprehensive, you could say a full stack framework. It's called LongVideo-R1.
LongVideo-R1. Okay.
And our deep dive today, it's all about how the system is built to let these VLMs perform genuinely advanced, pretty complex reasoning, but over long video content.
Right. Not just the short stuff.
Precisely. It tackles those limitations head on, the ones that have stopped AI from truly understanding things that happen over minutes, maybe even hours of footage. It's pushing the boundaries of what AI can really see and understand over time.
Okay, so let's really set the scene for you listening. Think about it. Why is understanding, say, a 15-second TikTok so fundamentally different from analyzing a whole movie or, I don't know, an hour-long StarCraft replay?
Yeah, what's the actual bottleneck?
What makes analyzing that 10-minute game or that hour-long vlog such a massive headache for AI? Why does it just seem to break down?
That really gets to the heart of it. And the research highlights a few key challenges. First off, it's about complex reasoning.
Okay, more than just object recognition.
Way more. It's not just saying that's a cat in a frame. Long videos demand understanding temporal sequences, how things change, how they evolve.
Like cause and effect over time.
Exactly. Think about predicting who wins a penalty shootout in football. You can't just look at the last kick. You need to consider the player's emotional states, their behavior, the momentum built up throughout the match.
Ah, okay. Subtle stuff.
Very subtle. And inferring hidden goals or strategies, like what's a poker player really planning beyond the cards they just played? Or precise spatial tracking. Imagine following a shell game. Where did the ball actually end up after all those quick shuffles?
Yeah, okay, I can see how that gets complicated fast.
And then there's comprehending the whole evolving narrative. Character arcs, plot twists, simple frame-by-frame analysis, it just can't capture that depth.
So it's not just about feeding the AI more frames from the long video. It needs a totally different kind of understanding, looking across time.
Precisely. Which brings us neatly to the second big challenge, data scarcity.
Right. You need examples to learn from.
And unlike, say, image recognition, where you have ImageNet, massive data sets, well, creating large, high-quality data sets specifically for long video reasoning is tough.
How is that?
Think about the human effort involved. Someone has to watch an hour-long video game replay and accurately label the hidden strategies or track the subtle shifts in the plot. It's incredibly time-consuming.
And subjective, probably.
Very subjective, yeah.
Yeah.
Slow and super expensive to do at scale.
I can totally see that. Like trying to annotate the subtext of every scene in a movie, exhausting. And then you actually have to process all this data.
And that's challenge number 3. The computational intensity, especially when you bring in reinforcement learning, or RL.
RL. Powerful but hungry.
Exactly. RL is great for teaching models complex goals, but it's notoriously resource-intensive. Apply it to long videos, it gets even worse.
How so?
You're processing these extended sequences of frames, right? Which means massive memory needs, much longer rollout times during training, where the model tries things out.
And that's where things crash.
That's often where they hit the wall. Researchers constantly run into GPUs just running out of memory. You hear it all the time. GPUs OOM with 512 frames.
Right. OOM with 512 frames.
I remember that bit. So these hurdles, complex reasoning, data scarcity, the sheer compute cost, they've really held things back.
Definitely. They've made it hard to build VLMs that can truly reason over long videos.
Okay, so we've painted a picture of a pretty big wall. How did this LongVideo-R1 team tackle it? Because it sounds like they didn't just chip away at it. They built, like you said, a full stack framework. What are the pillars here?
They were very systematic. Pillar number 1 is creating a really novel data set, the LongVideo-Reason dataset.
LongVideo-Reason, okay.
And it's not just about size, though it is large. It's specifically designed for reasoning over these long videos. We're talking 104,000 high-quality question reasoning answer pairs.
Wow, where'd they get all that?
It was curated from about 18,000 long videos from an existing dataset called Shot2Story, plus they added another 2,000 videos, high-res 4K stuff.
Covering what kind of things? Really diverse domains. Autonomous drifting footage, complex video games, household robotics, even wildlife documentaries. So broad applicability.
Not just one niche. And the questions themselves.
They specifically target 4 key reasoning types. Temporal reasoning, understanding the sequence of events. Goal and purpose reasoning, figuring out hidden intentions. Spatial reasoning, tracking things accurately in space. And plot and narrative reasoning, getting the story.
Okay, covering all the bases we talked about earlier. But how did they actually create these Q&A pairs? Manually? That sounds impossible at that scale.
Mostly automated, actually. That was the ingenious part. They had a pipeline. First, segment the videos into 10-second clips.
Right.
Then, use an existing VLM and VLA-8B to caption those clips. For spatial stuff, another model, VILA HD, generated object-bounding boxes.
Okay, getting the basic info down.
But the core reasoning generation came from a powerful open-source LLM, DeepSeek R1671B. It was prompted specifically to generate QRA pairs looking across the whole video. They guided it with phrases like checking the video or analyzing the scene to make sure the reasoning was tied to the visuals.
Ah, so using an LLM to bootstrap the reasoning data, but grounding it in the video content. Clever.
Very. And then another LLM cleaned up and refined the reasoning steps to make them clear and concise.
That sounds like a massive computational job just for the data generation.
It was around 80,000 H100 GPU hours, a significant investment, but it created this really high-quality foundation.
80,000 hours.
Wow.
And how do they use this data all lumped together?
No, they split it strategically. Around 36,000 samples were filtered as top-quality chain of thought, or CoT examples.
CoT, right, where the model shows its work, step by step.
Exactly. That was used for the first stage of training. The remaining 68,000 challenging Q&A pairs were reserved for the second stage, the RL part, and they even added another 102,000 samples from other existing video datasets to help the model generalize better.
Okay, that makes sense. Which brings us to the training itself. Just having the data isn't the whole story. You mentioned a 2-stage training pipeline. How does that work?
Yeah, it's a very deliberate strategy. Stage 1 is called long CoT-SFT. That's long chain of thought supervised fine-tuning. Think of it as the warm-up.
Using those 36K high-quality examples.
Precisely. The goal here is to give the model those fundamental reasoning skills, teach it to follow instructions, but specifically for these long video situations. It builds the foundation.
Got it. Laying the groundwork.
Then comes Stage 2. Reinforcement learning, RL, for long video reasoning. This builds directly on Stage 1. It uses an algorithm called GRPO, Group Relative Policy Optimization, chosen for its stability, and that bigger pool of data, the 68K challenging pairs plus the 102K extra samples.
And the goal of the RL stage?
It's about letting the model explore more freely, to develop more effective, more generalized reasoning strategies beyond the explicit CoT examples. It refines the abilities learned in Stage 1.
So they really complement each other. SFT teaches the basics, RL makes it smarter and more adaptable.
Exactly. CoT-SFT provides the structured intelligence, RL allows for refinement and generalization.
Okay, brilliant data. Smart 2-stage training.
Yeah.
But we still have that elephant in the room, the compute bottleneck. You try RL on long videos, rollouts crash, GPU's OOM at 512 frames. That was the wall, right?
The big wall.
But then
Yeah.
they designed MRSP. Tell us about this third pillar, multi-modal reinforcement sequence parallelism. Sounds complex, but this sounds like the key technical piece that makes it all actually work.
It absolutely is. MRSP is the crucial bit of engineering that makes training feasible. It directly tackles that computational nightmare, the massive visual embeddings, heavy rollouts, and long context LLM prefilling that just choked older systems.
How does it do it?
It cleverly uses sequence parallelism, basically splitting the work not just for the language part, but also for processing the video itself during both the rollout and pre-filling phases.
Okay, break that down. Roll out first.
Right. So, Stage 1, rollout with paralleled encoding. Instead of one GPU trying to process the whole long video, the input frames get evenly divided across multiple GPUs.
Like slicing up the video.
Exactly. Each GPU gets a slice and uses its vision tower to encode just that part. Then, an all-gather operation efficiently collects these encoded slices from all the GPUs and pieces the full video representation back together.
Okay, parallel processing for the vision part.
But here's the really smart bit for efficiency. These gathered video embeddings representing the whole video context, they get cached.
Cached, meaning stored.
Stored and reused for multiple rollouts within the same training step, usually 8 to 16 times. This avoids redundant re-encoding. The system isn't looking at the same frames over and over again unnecessarily within one update.
Ah, like the rap said, cached embeddings reused. That saves a ton of work. Faster, leaner, no okay.
Precisely. Much faster, much leaner on memory. Then comes stage 2, prefilling with sequence parallelism.
Okay, what happens here?
Those gathered embeddings, now representing the full video context, are padded and, again, partitioned evenly across the GPUs. This means each GPU only has to handle a portion of the full input sequence when preparing the data for the language model part for both the policy and reference models in RL. They leverage the VLLM engine here, too.
Sequence parallel prefilling VLLM engine fires.
Got it. So splitting the work again for the language processing part.
Exactly. The payoff is huge. MRSP gives them up to 2.1x speedup at 512 frames. And crucially, it lets them train with much longer sequences without running out of memory.
How much longer?
We're talking hour-long video-hour training, like 3,600 frames, on a single A100 node with just 8 GPUs. That's a massive leap from crashing at 512.
Wow. From 512 frames and crashing to 3,600 frames on one node. 8K frames processed without breaking a sweat almost feels literal now. Okay, that's genuinely impressive engineering.
Sure.
So what did all this achieve? What can LongVideo R1 actually do now? How did it perform? The results are really strong. First off, LongVideo R17B, the 7 billion parameter version, consistently outperforms its predecessor, LongVideo 7B, across 6 standard video benchmarks. Things like ActivityNet QA, Long Video Bench, Perception Test.
So better across the board on existing tests.
Yes. For example, on VideoMME, it hits 65.1% accuracy without subtitles and 71.1% with. But the really interesting test was on their own new benchmark, LongVideo-Reason Evil, which is designed to be much harder, focusing on complex reasoning.
How did it do there?
It scored 72.0% accuracy, which is significant because it not only beat other open-source models like Video R17B, but it also slightly outperformed proprietary models such as Gemini 1.5 Pro.
Wait, it beat Gemini 1.5 Pro on this complex reasoning task, an open-source model.
Slightly outperformed it, yes.
Yeah.
Which is a really big deal, showing the power of this focused approach.
That is a big deal. Can you give us some tangible examples? What does this improved reasoning look like in practice?
Definitely. There's a great example from a 20-minute StarCraft match analysis. LongVideo R17B could accurately analyze the player's styles, pinpoint specific strategic moments, and make a comprehensive prediction about how the game would unfold.
And the others.
Well, Gemini 1.5 Pro, while sometimes getting the outcome right, apparently had factual errors in why it thought that, and Video R17B gave more of a summary, missing crucial details from the video.
So LongVideo R1 had deeper, more accurate insights tied to the actual gameplay.
Exactly. Another cool one involved narrative reasoning. It correctly identified a man in a video as not being someone's husband by noticing the wedding ring on his left hand, a very subtle visual cue requiring inference.
Wow, that's sharp.
And there was a spatial tracking test, the moving cup example. LongVideo R1 accurately tracked the cup's position through complex movements, whereas competitors struggled with localization errors. It showed precise spatial understanding over time.
These examples really highlight that it's not just recognizing objects, but understanding relationships, context, and movement over extended periods. What about that frame scalability point? You know, the pushback. Long videos are just more frames.
Right, but the results refute that. They tested a smaller 1.5B parameter version, LongVideo R1 1.5B. It showed consistent performance improvements as the number of input video frames increases, hitting its peak at 512 frames.
And the baseline without the R1 improvements.
The baseline LongVideo 1.5B actually peaked at 256 frames and got worse at 512 frames. It couldn't handle the complexity.
Ah, so more frames only help if the model can actually reason effectively over them. It's not automatic.
Exactly. It proves that the reasoning capability unlocked by the dataset and the training pipeline is what allows the model to benefit from longer context. And the ablation studies confirm this too.
What did they show? They say it's just more data.
Right. The ablations show that just doing the CoT-SFT stage significantly improved performance, SFT alone lifts. Adding the RL stage on top pushed it even higher. RL pushes higher. It proves it's the combination, the sophisticated training, not just dumping more data in.
Got it. And handles long videos properly, 8K frames, configurable FPS, hour-long clips on 8A100s, and it answers the RL for videos is too slow, criticism with MRSP, faster, leaner, no OM.
Precisely. It addresses those key criticism with concrete results and technical innovation.
This really feels like a shift. You realize they didn't just build a better video parser, they built a bridge like between pixels scattered across time, and the stories, the strategies, the trajectories those pixels tell.
That's a great way to put it, and the implications are potentially huge.
Where do you see this heading? What's the broader impact?
Well, think about embodied AI and robotics. This is a big step towards enabling agents to sustain coherent, long-term understanding of their environment.
So robots that can actually understand complex tasks unfolding over time.
Yes. Robots that can perform multi-stage tasks, adapt better to changing situations, build richer internal models of the world for planning. That long-term understanding is critical.
Makes sense. What else?
Autonomous systems, like self-driving cars and maybe AR/VR, they need to understand sequences of events, track objects consistently, figure out cause and effect over more than just a few seconds. This helps build that capability.
And maybe less sci-fi applications.
Oh, definitely. Think about education. Imagine an AI tutor that doesn't just answer questions about a small clip, but can analyze an hour-long lecture video and provide truly contextual help based on the entire thing.
That would be amazing.
Or healthcare, assisting doctors or nurses in reviewing long procedural recordings, like surgeries, understanding the whole flow. Or entertainment, think super advanced sports analytics that grasp the strategy and momentum of an entire game.
The potential seems vast once you unlock that long-term reasoning.
It really opens up a lot of doors. Of course, as this tech advances, it's crucial to keep that steadfast commitment to ethical principles, privacy protection, and the broader goal of benefiting humanity firmly in mind.
Absolutely. Responsible development is key. So the next time you find yourself watching an hour-long vlog, or maybe a full sports game, just imagine an AI not just seeing the individual frames flash by, but actually understanding the entire unfolding story, the strategy, the trajectory, connecting those pixels across time. LongVideo R1 is showing us that future is closer than we might think.
It's a really exciting development.
It really is. So here's something to think about. What complex long-duration challenge in your life, maybe professional, maybe personal, could genuinely be transformed by an AI that truly understands the unfolding narrative of time? One that connects all those moments into something coherent and meaningful, worth pondering.
欢迎收听豆包 AI 播客节目。
Hello， 大家好，欢迎收听我们这一期播客啊。然后咱们今天来聊一聊这个非常有趣的话题，就是如何通过一些新的数据构造的方法和训练的策略，让我们的这个强化学习模型可以处理更长的视频序列，并且可以做一些推理的任务。
听起来很有意思。
对，
那我们就直接来看看这篇文章是怎么解决这些问题的吧。
好，那我们来第一个问题啊，第一个问题是这篇论文提到了哪些领域的相关工作？
他们就是提到了多模态推理模型，然后序列并行化，以及大语言模型和视觉语言模型的强化学习框架
啊。那这个 LongVideo-Reason 这个数据集是怎么构建的呢？
它这个数据集啊，就是分为几个部分，然后其中比如说在强化学习里面用到的这个数据子集啊，它是有68K 个 比较有挑战性的这种长视频的问答对。这些问答对呢，就主要是用来在模型的第二阶段去提升它的这种推理能力的。另外呢，他们还从其他的数据集中引入了102K 个高质量的开源视频，这些视频呢就大大增加了模型的这种泛化能力。
哇，这数据量真的不小啊。
对，
那这些数据具体是怎么用的呢？
就是在第一阶段的这个推理能力的 warm-up 训练当中啊，这些额外的视频数据就提供了非常丰富的资源，然后让模型去学习。到了第二阶段的这个强化学习的时候呢，就主要是用那 68K 的这种问答对去专门的提升它的这种推理能力。
这个长视频的推理数据
对
是怎么自动生成的呢？
他们这个方法就是先把这个长视频切分成10秒左右的这种短的片段，然后呢用 NVIL8B 模型啊去给每一个片段生成一个描述性的 caption。对于一些需要空间推理的这种视频呢，他们还使用了 VILHD 模型去生成一些物体的 bounding boxes，再根据这些 boxes 和 captions 去生成一些空间推理的这种问答对。
哦，听起来很系统啊。那这些问答对是怎么来的呢？
就是他们用了一个非常大的这种开源的推理语言模型，叫 DeepSeek R1671B， 然后呢，去根据这些 captions 去生成4种不同类型的推理的问答对。这些问答对呢，又会经过一个语言模型的 refinement 去优化它的这个推理的步骤。最终呢，他们还手动的整理了1000个比较高质量的这种复杂的问题，组成了一个新的评估基准，叫 LongVideo-Reason eval。
那这个LongVideo 的这个训练的流程，特别是这个 LongVideo R1， 它是怎么设计的？
它这个其实是有2个大的阶段，然后第一个阶段呢是一个 warm-up 的阶段，就是用了36000个高质量的这种带有 step-by-step reasoning 的这种数据，在一个叫做 MMSP 的系统上面去做一个有监督的精调。那这个就会给模型一个基本的理解长视频并且进行推理的能力。
哦，那第二个阶段呢？
然后第二个阶段呢是一个强化学习的阶段。那这个阶段呢就是从长视频里面去选取一些比较密集的帧，继续去优化这个模型。那这2个阶段结合起来，就会让这个模型在长视频的这种推理任务上面表现得更好。
这个 long video code supervised fine tuning 这个具体是怎么做的？
就是它用了104万高质量的这种问题推理答案的3元组，然后呢，经过一个 filtering 的方法啊，最终选取了36万个样例，在这个 MMSP 的这个训练系统上面去做一个有监督的精调。那这个就会给模型一个基本的理解长视频并且进行推理的能力。
那这个 GRPO 这个算法在长视频领域是怎么应用的呢？
他们就是基于这个 GRPO 的框架，然后去做了一些多模态推理的训练的探索。那整个的这个训练过程还是按照这个标准的 GRPO 的算法去进行的。
OK 了，行吧。然后今天咱们就是聊了聊这个如何通过一些新的数据构造的方法和新的训练的策略，让我们的这个强化学习模型可以处理更长的视频序列，并且可以做一些比较复杂的推理任务，包括这个模型的训练的流程啊，这个数据集的构建啊，真的是非常非常细致和有创新性的一个工作。
OK 了，以上就是这期播客的全部内容啦，感谢大家的收听，咱们下期再见，拜拜。